Good day, hello there. My name is Desmond Aubrey. I'm an independent researcher in terms of heat transfer and thermofluid technologies, and I have a passion for computational fluid dynamics. I have done a lot of research in this area, and one of my topics that I've been studying towards a PhD on is the wave nature of the Navier-Stokes equations. So what I'd like to do is to actually go through this video that I've put up on YouTube and just talk through what you're actually seeing, because for a lot of people it might not make a lot of sense, but I'll talk you through step by step and let's see if we can learn something together. So first off, at the top we have the velocity magnitude plot. What this does is picks up the velocity in the x direction and the velocity in the y direction, and it then computes the velocity magnitude. And the colors, basically high velocity magnitude will be red and low will actually be blue. And below that we have the acceleration diagram. Now when we talk about acceleration, if you look at the Navier-Stokes equations and the way they were derived, we talk about, let's call it the total acceleration. Mathematically we talk about the total acceleration, and what that does, it has a time component which we call the temporal acceleration, and that's basically the derivative, partial derivative of the velocity vector with respect to time, and then we add that to a convection component. Now the reality is the way the Navier-Stokes were constructed is constructed as a force balance. It comes from Newton's second law. And so we end up with the situation where we have time in the temporal part of it, so the temporal acceleration, and then with the convection part actually implies the spatial, the movement in space, the acceleration in terms of space. Okay, so you've got temporal as well as space components, and these are actually components of force. It's a force balance, but what happens is we then divide by the mass at any particular stage, and what do we have? We know from Newton's second law F is equal to ma, so if we divide F by m we end up with A, which is acceleration, the total acceleration, which implies the total force balance because they're proportional to each other, just the constant of mass is there. So if we understand the acceleration diagram, we're going to get a pretty good handle on what the forces are and what's really going on. So first of all, what we have, if we just follow the cursor, if it makes sense, we have an object, in this case a cylinder. This is a two-dimensional plot. It's a cylinder, so we're constraining movement in the plane, if you want to call it that, two-dimensional plane. And then we have it sitting inside a duct. Now, to the best of my knowledge, I've not seen much work in this area at all, and it's been my passion. I've been trying to understand what is behind turbulence, as we call it. And what you're going to see come out of this discussion is something very interesting. You're going to see patterns emerge, because that's what I look for, are patterns, and trying to explain what these patterns are. What do they represent? So let's take a walk through the simulation. The first part is we've actually got to get this velocity. We start at time zero. The velocity starts to move through. The velocity field moves through. And we start to go, so we have what we call a transition time, where we get lots of change in time. And then at a certain point, the change in time, once we've got this, let's call it velocity initial wave through the system, we start to see the spatial component or the convection component coming in. Now, what's interesting, when you do most CFD work, you find that it's very unstable. Because, and people always complain about the convection term, there's a slight non-linearity in the Navier-Stokes equation. Okay. And so you have velocity dot product with nabla v, which is change spatially of the velocity field. And this tends to throw a lot of people. Now, I simulate in a way which I never blow up. I haven't blown up a simulation for, I don't know, 15 years. But I've got some tricks up my sleeve. So let's get this thing to start moving through, and I'll comment as we go through. It's a bit of a long video, but I think it's worth looking at. It starts to put things in perspective. So let's start to play. So just before I do that, this is the video that I'm analyzing here, vmag.act at Reynolds number 150. And we can start to understand. So let's start to play. Let's have a look. So now what happens is we start to get the velocity goes through. What starts to happen is this object gets in the way, and we start to create accelerations around the object and starting to get a velocity field. So we get a high velocity here, which you'd expect, because it's a constrained space. And behind it, we have this very nice shape, which is actually very, very low velocity. But if we look at the acceleration diagram, you start to see an interesting, in other words, there's a lot happening at the front here, obviously because it's stopping. Acceleration or forces pushing back. This object is pushing back against the flow. And then you'll see as this accelerations here start to move, and they'll move down and they'll start to change shape. And what it does, it keeps going symmetrically up to a certain point, and then we start to lose the symmetry. It starts to break symmetry. Okay, until then it's balanced. So let's carry on a bit further. And here it goes, here it goes, here it goes. You start to see things happening over here. They still look fairly even. If we look at it over here, we start to see the structures still look fairly nice and even. Nothing's gone silly yet. We start to look at these fields here. Still everything seems to look okay. The rest of the flow field is already advanced down here. And let's go a little bit further. And continues. It still looks fairly symmetric. We start to see symmetry here still. This flow field looks quite nice. If you look at both of them, it doesn't look like there's much change. This is the kind of plot you often see in people's CFD work, and people get a lot of pride in plotting these things. But the reality is, what are you trying to really get from it? All right. So I've built up the theory understanding the accelerations because that makes sense to me. If I understand accelerations, I understand forces. So let's carry on a little bit further, and let's see what comes out of it. So it's tracking now, tracking, and then suddenly what we start to see is an imbalance between the top and the bottom. That's telling us something. We're starting to break symmetry. So a concept certainly in not chaos theory, but certainly in physics, is things stay symmetric. Once they break the symmetry, we start to get something interesting happening. All right. So let's, by the way, before I continue, I don't know why this thing keeps coming up with vectors, but if you, most plots, people talk about a steady state. Now, in reality, in a flow like this, there is no steady state. This is a transient analysis. And if it doesn't stabilize and stay something like that, or with symmetric flow fields, then we'd say, well, it's not, there is no steady state solution. So at universities, very often what they do is they say, okay, fine, we'll drop the dVdt component, the temporal component, and then we'll just work with convection. That's not physics. That's not physics. And we get some really dumb answers. And so pretty pictures, but it doesn't tell us much about the physics. All right. So let's go a bit further, and let's see what happens. So now we're starting to see things starting to get quite rapidly changing over here. We're starting to see interesting wave formations forming. Top and bottom are no longer the same, and we can actually see a change here. This part here starts to change shapes, and we start to see lumps occurring, velocity high spots, if you want to call it that. But certainly in the acceleration diagram, things are no longer symmetric at all. So the forces are not symmetric. And then you start to see further. Now you start to see some patterns emerging. All right. And you see patterns starting to, lots happening here. We're getting areas of high force, okay? And look what's starting to happen here. Very much a broken situation. It's now moving into another state. Okay, this is the what we see whenever we get to a dynamic system. We get different types of dynamics that emerge. Islands of dynamics, if you want to call it that. And so steady state, it may be one of them, but in the transient analysis, you start to get a number of different states, and then it kind of stabilizes on something. But that's not a steady state. That has a time or temporal component built in. So we see all this happening here. Things are changing in time and in space. Let's just carry on. So here we go, carries on. Carries on, and now we're starting to see some interesting things occurring. We're starting to see some round shapes occurring at the back here. All right, what are these? In the center are very, very blue spots, which means, in fact, you're going to find out later, these are actually singularities. In other words, they're a center of something where we have zero acceleration. The forces kind of cancel each other out. And around them we have something, all right? And at this point, the velocity diagram is the velocity magnitude is starting to give us all these chunks that are flying off it. Most analyses, we see this stuff, but we never look here because we just haven't, nobody's built these equations. I build them and then I actually put it into my simulations and force it to give me the answers. You see, when you run a simulation, what are you getting out of it? In this kind of thing, we're getting x velocity, y velocity, pressure, and time. And from that, we can build all the equations that we need. And then we can just analyze them visually. So what I do in my simulation work is I analyze what am I seeing? It's a visual experiment. And then I try and make sense out of it. So let's go a bit further. All right. So what's happening now? Now we're starting to get these structures, and they're starting to, interesting, they're starting to take some kind of shape here, some kind of form. It comes off the back of the object, and it's nice and straight, and then we start to see this happening. Okay? And let's carry on a bit further. Right now, the velocity is not telling you very much. It just tells you there's chunks of high velocity. What does that mean? Okay? And interestingly enough, you can try and line these up if you want to. And you'll find the high velocity here, got low acceleration there. And let's continue a bit further. Carry on. Now we're starting to see some structural formation. The back here. Look at this. Look at this. Look at this. We're seeing structural formation. So we can let this thing run out. What's happening is you'll see we're moving into a different state. It's not steady state. Cannot be, because it's changing in time. Okay, it becomes a spatial configuration. Now remember, what's happening here is you've got constraints. You've actually got sides to this tube or duct, if you want to call it that. So these objects or these accelerations or force balances can't escape. They are kind of constrained by what's happening here. And let's let it go further, and then we'll start to discuss further what we're seeing. So let it just run. And we're starting to see a consistent pattern now. Every time it's spitting off, and then it's going into a structural situation. So what you're getting is you're spitting off the back here, and then you're moving into these patterns. Now, if we were to talk about vortices and vortex streets, this is what this is. This is what this is. So it's actually a vortex formation, but they've been locked into a certain configuration. In other words, what you've got actually is a triangular configuration. So we've got, this is the one vortex, this is the next vortex, and they're actually opposites, okay? And you get this vortex street. And the vortex street is determined, people talk about, oh, vorticity and all this. No. Go back to Newton's second law. What are we dealing with? We're dealing with accelerations. Accelerations proportional to force. So we're seeing force balances. And these kind of singularities, the forces literally cancel out. But the force structures eventually force themselves, these things, they have to create a situation where the forces actually balance. Okay? And you'll find that's why they create these structures. They're actually quite fascinating. And let it run a bit more. And I think you're going to see that eventually what we've got is a consistent situation where we end up with these rear force structures, which we know essentially as a vortex sheet, okay, or a vortex street, should I say. And you'll see a lot about it in the books. The mathematicians, they don't understand the physics, so they talk about vorticity and all this. That's false. It just gets you confused. The idea is to look at the physics. My background is I studied engineering in South Africa, and our degree started off as physics based. In other words, you get a Bachelor of Science Bachelor of Science. So first of all, you're a scientist. Our first year was all science and maths. And at the end of the first year, we had the option of actually going and continuing to become a physicist, which was a 3-year course, or we could continue and start to branch into engineering, which is a 4-year course, an honors degree, and start to really apply. So it becomes applied physics. Many of the modern ideas, certainly the American way, and that is they use mathematics as the base. So they don't actually understand the physics of what's going on. So my project has really been to try and understand the physics of this whole situation. All right, and I think this is very important to understand. So let us run through a little bit more, and then we'll wind it up. So basically what's starting to happen is we're getting these patterns at the top sheds, the bottom sheds, the top sheds, the bottom sheds. So what's happening is we're getting instability on the front here, and it's shedding. The back field is also affecting what's happening over here. People keep saying, oh, well, there's no, you don't get a link backwards. I always say you don't get a link from here to there. It has to always go in this direction, in the forward direction. But that's not actually true. You'll find that the velocity field is determined at the back end, and that actually does have an impact on what's happening at the front. And so you'll find that a lot of these flow stabilization mechanisms that people talk about, which are there to try and stabilize the convection field, which is slightly nonlinear and tends to blow things up in simulations. I remember one chap saying to me, no, the whole field must go in this direction. That's why. And I said, no, it's not true. In reality, you're going to find the back actually does influence the front. And these structures actually have an impact on what goes on there. And so those structures then force it also to oscillate over here. And you'll see even at the front edge area, you see you're getting stuff going up and down. So you're actually getting a signal moving from the front to the back. This input signal here is a constant acceleration. It's not a variable acceleration. But what's happening is the actual flow field is forcing the front acceleration to kind of move up and down, which is interesting. So we're actually getting a backward communication in the system. This is very important. So people, like to say that everything must be flow stabilized this way, and you'll find the different techniques that people come up with, constant volume and so on. They end up with all these discussions, but it's not actually true. The physics actually doesn't need it. And if you look at the velocity diagram, it's very interesting. You're starting to see these different pieces breaking off at the back. Actually, if you do I do quite a few things. I also look at the actual loss of, let's call it loss of energy in the system. And you plot that. You can also plot vorticity, if you like, at the back. Viscous dissipation is one thing I play with, and you get some amazing patterns that emerge, and they correspond quite nicely to these structures here. So really what I wanted to talk about today was an understanding of what this acceleration field is all about. And I would encourage people who are researching in the field to understand, because once you understand the forces, so just to reiterate, the build-up, the derivation of the Navier-Stokes equations, okay, it starts off as a force balance. Newton's second law. Force is equal to mass times acceleration. So what we have is we have the acceleration field, which itself is composed of two parts. A temporal part, a change of velocity with time, plus a convection part, which is velocity dot product with nabla v. Nabla v is the change of velocity in space. So we add the two together, we end up with total acceleration. That's equal to F times, is equal to F divided by M, which is the mass. And the mass, you'll find, if you've got yourself a nicely structured flow field, is reasonably consistent. So there's important tricks on how do you set up these simulations, and it gives you decent results. And most people typically, they don't understand things, and they end up locking, letting time go variable and all kinds of things to try and, so to say, stabilize the solution. But all you do is you wipe out the physics when you do that. So a lot of these so-called top-end CFD software packages you get actually lose the physics because they're trying to flow stabilize. They just haven't got an understanding of the physics properly. And so when I got into this work, I started to experiment to get to a point where I wanted to understand the physics and the flow fields. And as I say, once I got that sorted out, I didn't have any problems after that. I didn't have any blow-ups. I didn't have any silly situations that occur like most people have, okay? So I don't get all that. So what I'll do over a period of time, I'll put in a little bit more discussion behind some of these flow situations, simulations that I've done, and talk through what's going on. You'll see I've also got, just for a punt for some of the work, I've got a website called RareTechSEA. So that stands for Rarefied Technology Southeast Asia. It's the short form of it, okay? And this, I've been in this game, heat transfer game. I've been in the game since 1985 or just before. I've been all over the world. What happened is I studied Bachelor of Science Engineering, and then in mechanical was my speciality. But in mechanical, we had just at that stage, firstly we had thermodynamics as the basis of what we learned. And thermodynamics is really a point-to-point analysis of energy changes and so on. And at that point, heat transfer just came in. It was a new course in my final year, and I loved it. And we just come out with the book, the first course, certainly at our university, on heat transfer. So I lapped this thing up. And I loved it because when we talked about things like heat exchangers, the heat exchangers themselves are very, very complicated. The equations that govern the heat transfer. And this got me really very interested. I like the complexity of all of that. You've got heat transfer, let's say, in a tube, and you've got heat transfer in a shell. And what equations govern. You've also got a heat transfer through the tube wall. And then what helps with that? And then you get things like fouling. You get layers that build up on either side, and they affect the heat transfer as well. And the heat transfer equations are actually non-linear. There's three equations really involved. And I'll do another series on that and discuss what we call heat balance and so on. But this is my speciality, so I consult in this area. I've been, in my earlier years, I've been around the world a lot at one stage, through over 36 countries. And so, but at this stage, I live here in Vientiane in Laos. My wife is from Laos, and COVID came along, and it actually hit me very hard. I had COVID Delta. I was teaching in a very high density situation, and I ended up with a very high viral load, and it hurt me actually. I got very damaged by COVID-19, and then followed by long COVID, and I was essentially almost my legs were paralyzed for about 9 months, and I recovered, and I've had to fight my way through it. So life has its adventures. So it means that I'm home based now. I can't travel like I used to travel before. So I've kind of been putting a lot of time in now into a lot of my research work and so on. And I've written papers on some of these subjects, and you can look it up under the wave nature of Navier-Stokes equations, and look up under my name, Desmond Aubrey. Vixera, for instance, I put stuff up there. One of my reasons why I put Vixera, and also there's a few others I put my information up, is I don't like all the censorship that you get from these what would you call it, these publishers, because they make money out of you. You've got to pay a lot of money for you just to get your paper published, and then you've got people who really don't understand the subject. And when you're breaking new ground, people don't understand, and so they try and cut you back and start to control what you're doing, and it's just not possible to break new ground like that. So I publish openly, because at some point it will make a difference in the world, but not through this peer review. How can you review through peers when your peers don't understand what they're doing? It just makes no sense. They get frightened, and then they try to put you into what they understand, and it doesn't make sense. So we can play out the back end of this movie. Let's just see if it still carries on, and you'll find it's moved itself into a situation where we've now, we've got effectively a regular pattern geometrically up in this area here, geometric pattern, but we've got time variation up here. So this is the true acceleration or total acceleration. Okay, so for this situation there is no steady state. Steady state would imply there's no change in time. but there are changes in time. So I would say to folks that learn at university, tell your professors that you must do transient runs. What is a transient run? It's actually doing a snapshot in time. So it will add a certain time step, a certain time, it will take a snapshot for you. Then it will advance and take another snapshot. Advance, take another snapshot. Then effectively you link all those frames together till you get to a movie, and then you understand the dynamics of what's going on. So anyway, that's just a bit of background. I'll talk through later some of my other videos and try and give a bit of background. Anyway, as I say, thank you very much. I hope you enjoy what you see. If you find it a bit long, all right, sorry about that. But there's a lot that I want to go through. Okay.